Okay, so this final session, our first speaker is Jacobstein. He is the CEO of Technology. He's been in the AI field for quite a while now. He's also been involved with molecular manufacturing, the original work of Eric Drexler. He's been involved with the Foresight Institute, or Foresight Nanotech Institute now. He was involved in the early stages of, for example, the Foresight guidelines on molecular nanotechnology. And he's done a lot of great work in the field. He's going to be talking about how there are many examples of innovative AI applications right now and what that might hold for the future of the field. So take it away, Neil.
Thanks, Tyler. I think we don't have an either-or choice between AGI and narrow, specialized AI applications. We've had 50 years of artificial intelligence as a field, 50-plus years, and we've had 50 years of impressive hardware acceleration. And we still don't have AGI, not even a weak one, like the HAL 9000 from 2001. In spite of this, I'm quite sure that the question is when and how we'll have AGI, not if. NASA has already built many excellent early AI systems that monitor spacecraft system health and control spacecraft operations. Alas, these systems don't lip read, they don't ask charming new questions, and they don't have psychiatric problems. Early AI applications were largely built to solve specific industry or government problems. Many perform complex tasks that only humans, fairly capable humans, once did. And most are not attempts at artificial general intelligence. There are a few exceptions. SOAR, Psych, Novamente, COG, others. But most of these systems demonstrate limited and narrow learning ability, if any, even when they incorporate machine learning modules in their operation. They're minimally self-reflective, but they're often goal-directed. They use goal-directed inference. Many of these systems are no longer just narrow expert systems, as you'll see. Many have complex components and hybrid designs, and they've now migrated to the web. Google Search, American Express credit check for risk analysis, Babelfish's language translation. And there are lots of beliefs floating around about AI. Here are three of them. One is, if it works, it isn't AI. Many applications work quite well using simple AI techniques. In addition, specialized AI applications are useful, effective, and yes, limited. That's okay. Another belief is that AI is all hype. It's boom and bust from the 1980s. And although there was a lot of that, early AI is in routine use in many domains. It's already produced billions with a B worth of value. And writing off AI is a little bit like writing off e-commerce after the dot-com meltdown. Other people believe that if we're not talking about human-level and greater general intelligence, then we're really not talking about AI. And to that I would say specialized AI applications routinely outperform humans on narrow tasks. That's interesting. And there are many types of AI, a whole continuum of types of AI with different capabilities, just like I think there'll be a continuum of different types of AGIs with different capabilities. And I believe that there's no one true path to artificial general intelligence. A lot of this is about expectation management. New technologies tend to arrive late. The problems are hard, often harder than we thought. And as Paul would say, clarity of vision is not proximity to goal. Sometimes it's easy to confuse the two. And many technologies start out overhyped. AI certainly did. And our planning horizons are woefully short-term. Eventually, technologies like AI do deliver more than expected. And that's because technology acceleration, particularly of the double exponential kind that Kurzweil talks about, is not intuitive. including to practitioners in the field. They often underestimate how quickly a technology can arrive after 25 or 30 frustrating years of slugging it out in the trenches. And we tend to see future possibilities through today's biases and filters. New technologies lead to transforming applications, not just faster and more of what we currently have. It took nature 600 million years to go from multicellular organisms to human-level AI. And from that perspective, all the arguments about will it take 5 years or 10 years, 20, 25, 50, are in the round-off error. The Association for Artificial Intelligence's Innovative Applications of AI conference showcases deployed and emerging applications of AI. They've been doing this since 1989. 384 applications have been showcased during that period, and it's primarily about hybrid knowledge systems. Let me tell you what they have in common. They all utilize some form of inferential reasoning and knowledge. They get their problem-solving power via domain and task-specific knowledge. And unlike AGIs, the knowledge is engineered by humans rather than learned. And that's also true when machine learning components are incorporated. Some of that knowledge is gathered by machines, but often a lot of the initial conditions are set up by people. These systems are now integrated with enterprise components. They're embedded in products and services. They cover a wide range of domains. They're globally distributed. They span a large number of tasks, a diverse set of users. They're implemented on client-server PCs, PDAs, and web services. And they are just useful applications with no particular AGI agenda. So here's a sampling of application sponsors. I think there were 154 by 2006. They include a large number of Global 1000 companies as well as government agencies. And there are quite a few countries that have submitted papers to IAAI. And this actually underrepresents all the talented researchers from all over the world who've published under the auspices of US institutions. I did a little study of the application domains, or the areas of focus of these applications. The ones between 1989 and 2006, there were 362 of them. And the most common area was computers and software engineering, not surprising, followed by manufacturing, military, finance applications, business operations, telecommunications, arts and media, healthcare, space, ground transportation, airlines, education, sales, biotech, energy, emergency management, insurance, security, intelligence analysis, construction, law, agriculture, chemical engineering, configuration, and cost estimation. Oh, let's go back here. Biotech, energy production, emergency management, insurance, security, intelligence analysis, construction, law, agriculture, chemical engineering, paleontology, and treaty verification, a couple of those. The next slide is on the tasks that these systems perform, and they include this long list, lots of different tasks, and you can see that they're clustered primarily around planning and scheduling, data interpretation, information retrieval and classification, performance optimization, et cetera. When we consider the value added by AI in these applications, they're in augmenting or replacing human skills, which allows you to improve accuracy and consistency. They accelerate process timing. They improve products and service quality. That increases productivity. It allows you to decrease costs. It expands the range of the possible. It doesn't just do more, faster, better. And it helps institutions manage their knowledge. Let's look at just two of the very early systems that were expert systems. Here's one that was built for British Petroleum that does microfossil identification associated with rich oil fields to drill in. This system was basically constructed to eliminate delays in the process of figuring out where to drill. 1 day of delay cost $1 million. British Petroleum reported that one particular delay cost them $15 million. And the VIDES system, the Visual Identification Expert System, acts as a domain expert assistant or a member of the team. And it's virtually eliminated identification delays. It's implemented on Lisp and Key. Key is a knowledge engineering tool on a Sun workstation. And here's a pitch expert. Pitch is about 4% of cellulose. It's a sticky, resinous substance that tends to gum up paper mills, pulp mills. This system was built for the Canadian pulp and paper industry. It's a process control advisor. It includes a mill model and a diagnostic problem-solving model, and it recommends actions to reduce costs, largely costs of repairs and delays. It was implemented in a knowledge engineering tool called ART, and also using Lisp and Sun on a Sun workstation. And it was implemented in 36 paper mills at the time of publication, saving an estimated $28 million. So in terms of the very early parts of the conference, a lot of the systems were delivered standalone on Lisp, and as Rodney pointed out, Lisp is still used today, and it's very productive, and high-end workstations. And a lot of these systems were built from the ground up, and they used very complex tools that subject matter experts really didn't like. Even if an application has AI in it, it often has 85% system engineering code and other conventional components, and only 15% AI. And a lot of the early applications were delivered with AI as the central focus of the system. A lot of these systems are not properly integrated with mainstream applications. They tend to be narrow and brittle expert systems. They generated considerable value added, however. Many of the systems were hard to maintain. They were delivered by researchers from the outside, kerplunk, and they were delivered into weak knowledge management cultures. Here's a system that was not in the IAAI conference, but a really interesting system called the Dynamic Analysis and Replanning Tool, DART. It was a military logistics system that was built for DARPA by a team of contractors that included BBN and ISX and others. It was used in the 90s during the first Gulf War. It focused on the logistics of materiel transfer between Europe and Saudi Arabia. And it had 3 key components in it: an AI planner, a database forms generator, and a linear programming module. It was the poster child of DARPA's 1990 planning initiative. And a comment from a former DARPA director, Vic Reese, was that the DART scheduling application paid back all of DARPA's 30 years of investment in AI. It's now been 40+ years, and DARPA continues to be a very big investor in AI, and in applications that have particular military significance. Rod mentioned some of them. You can also look at the DARPA Grand Challenge as another direction that the agency is going in. Here's an example of a system that's been around for a while. This system was published on its 10th anniversary in 2004. It's a GE Plastics color formulation tool. It's a case-based system that matches color to GE's vast inventory of polymers and dyes. And it saved 22,000 hours annually. It's in active use all over the world. They ported it to the web under the Color Express Select name. It saved millions of dollars in productivity and materials. It's an example of an incremental innovation in a company that pays huge attention to process issues. And here's one from the 2006 conference, CombinedNet ASAP. This system is focused on the multi-trillion-dollar procurement industry, and it used heuristic constraints and sophisticated tree search to optimize the procurement process. Specifically, what it did was increase the expressiveness, the efficiency, and the granularity of the specification of supply and demand for very complex auctions. They hosted 230 procurement events, $16 billion worth of transactions, with documented cost savings of $1.8 billion. Well, I think they're getting somewhere. Here's a system that did on-demand, web-based ASP products, a number of different ASP products, and they hosted on a 64-bit shared server farm. So in terms of where we are today, AI is often delivered with other components, as well as multiple types of AI components. And in addition to Lisp, there's a heavy use of mainstream languages like C++, Java, Ruby on Rails, Python, etc. And the use of Web 2.0 standards like OWL and Swirl, deep integration with mainstream systems instead of grafting them on from the side, browsers as the standard GUI, delivered on a wide variety of delivery platforms, now user-centric applications, and more attention to the target context for delivery, the process issues. So let's talk about what didn't work. A focus on AI tool features versus the underlying power of the knowledge. There was difficult knowledge base reuse across time and institutions, and that's still a problem today. There were high maintenance costs, particularly if the knowledge changed rapidly, and AGI could help solve that problem. Open loop R&D was not particularly productive. It was better when it was driven by real-world feedback. Poor integration with mainstream software, grafting it on from the side, caused all kinds of problems. Rapidly evolving heterogeneous infrastructure and platforms causes everyone problems, including AI applications. Weak business processes in the target institutions, including rotation of champions, weak knowledge acquisition tools were a problem, and limited learning capabilities, forcing a lot of manual input. Again, something that AGI could address. So we've talked about knowledge engineering and system engineering tools. Let's talk about some of the cultural issues. I like to use the analogy of Frank Lloyd Wright's Falling Water Home. Here's a brilliant designer working with highly skilled technicians, using exotic materials, doing one-off, very complex integrations, and they delivered the system late. It was over budget, and the system was buggy. And of course, the designer attributed any weaknesses in the system to the weaknesses in the user. That may sound familiar to you. Let's contrast that with the continuous improvement methodology that Toyota uses to develop the Prius and the Lexus. They have documented incorporating over 20 million suggestions over just a 40-year period. It's now a 50-year period. I don't know what their new number is. But here's a culture that uses both AI and 3x5 cards to manage their knowledge, and they take it very seriously. It's a very big deal, and they end up with products that reflect the kind of continuous improvement that they do. So in terms of what worked with the IAAI applications, real-world testing and experimentation, solving customers' pain point problems, capturing stable problem-solving knowledge because of the limitations in the technology, systems that perform one or more specific tasks. It could be more than one task, but then you have to have deep domain knowledge to go after the additional tasks. Combining AI with other technologies like statistics, optimization, simulation, using standard application infrastructure, getting rapid, high-volume signal-to-symbol interpretation so you get very rapid transformations and users don't have to wait, attending to user, cultural, and process issues, finding champions and top management commitments, and improving systems continuously. So let's look at the evolution of semantic web services. We already see web data are becoming tagged, active, and reusable. We have dynamic semantic service layers that are beginning to do interpretation and recognize patterns. They're going to be building context models of users and tasks and domains. And we'll see web service assistants and associates proliferating. They will do association, complex modeling, and prediction. We'll see the extensive use of HTMs, hierarchical temporal memories, like of the kind that Numenta's NuPic program provides, and other cortical software. We heard about others here. And we'll have immersive experiences in 3D semantic space, not just zooming around in VR, but actually being able to interact with and query the objects in the space, talk to the Sphinx, and learn about Egyptian history. So one of the things that we see now, Ben will be talking about this a little bit later, is that the ability to embed these systems is very important. Embed knowledge application systems in these VRs. So 10 rules for building AI applications. Balance long-term vision and pragmatics, still important even if you're thinking about AGIs. Distinguish technologies from market applications, also important because of the pressure that researchers get to bring products to market very quickly, like in a 3 to 5 year time frame. Test ideas and code against real-world problems. Leverage web economic standards and open systems. Utilize complementary technologies and hybrid applications. Leverage domain and task-specific knowledge. Assemble systems from robust components instead of rolling them all individually. Develop applications that learn and improve, do extensive user and consequence testing, and develop AI roles where the AI gets increasing responsibility based on its behavior, going from an apprentice to an associate to a partner, and then perhaps more. So one possible scenario for the future, we might see a rapid increase in hybrid AI web agents, intense economic and social selection pressure on the web, agent cooperation and competition simultaneously, applications that learn and improve continuously, a vast increase in machine-to-machine agents without humans in the loop, maturation of neuroscience-inspired agents, selection for useful new non-human tasks, tasks that humans just completely out of their range, embedded values, principles, ethical principles, and layers of control, agents as apprentices, associates, and partners, as I've mentioned, and the emergence of AGIs with vastly different capabilities, different AGIs with different capabilities, and radically new applications, risks, and opportunities. Any questions?
Thank you, sir.